Gives me great pleasure to introduce our next speaker, who really needs no introduction. I mean, literally as seen on TV. Hopefully you guys all had a chance to see the movie one night this week. So we've got Dave Silver, who's going to be talking to us about reinforcement learning. He's the head of the reinforcement learning group at DeepMind, and he's done all sorts of things. He got his PhD with Rich Sutton at the University of Alberta. Before that, he had a startup doing games, and his undergrad is from the University of Cambridge. He's done all sorts of exciting things, like being involved in some of the initial Atari work. Everybody should know his work on AlphaGo and AlphaZero. So really quite a lot of accomplishments. And then just one last thing that I think is really cool is he's actually kind of one of us. So both of his parents were born in South Africa. Don't know how many of you knew that. So yeah, I'm really looking forward to this talk, and it's really great that you're here. Thank you.
Okay, thanks for the great introduction, Benji. It's really a pleasure to be here. Thanks so much for the invitation. What a super event. I mean, it's just so special, just feeling the energy around here and being with you all. And I hope to meet more of you. Once the talk's out of the way, I'll hope to chat to many of you in person. So I'm going to give a talk entitled The Success Stories of DeepRL. Benji asked me to give a talk, and it could be on anything, but just make sure it included something about AlphaGo and so forth, because people would want to know about it. And I thought it would be fun just to expand it a little bit and try and give an overview of what's been happening as this field of deep reinforcement learning has exploded and started to see a lot of success. Now, I hope you'll forgive me in the hubris of including some of my own work in the success stories. But I feel like it's the work I can talk about the most effectively and communicate the clearest, and so there is some of that in there. But I've also tried to include work from all over the place because, as you know, this has really taken off, and there's labs in academia, in industry, all over the world, and now including Africa, all kinds of great things happening, and I hope to see more in the future. So it's really also, I just want to say, it's really a very personal view. So if something isn't included here, that doesn't mean it's not a success story. And I had to pick out a small number of things to focus on in this talk. And depending on how time goes, I've got actually a follow-up talk, which I may have time to give, which tries to tie things together a little bit with a second kind of view, which is like the principles of deep reinforcement learning, which is kind of my personal view of the lessons that we can draw so far on what ties together these successes and how we can have more, and perhaps some things to take away in terms of what advice you could take out of what we've seen so far in DeepRL. So that's the plan, and I hope there's a little bit of time for questions as well, and we'll see how it goes. Okay, so reinforcement learning. I think we need to start by understanding what do we mean by DeepRL? Like, what is this thing called DeepRL? What's special about it? And so to understand DeepRL, we need to understand the two components. We need to understand deep learning, and we need to understand reinforcement learning. And so the way I view reinforcement learning is it's a very general purpose framework for the whole of decision making. So really, RL is really trying to get a core science, which is the science of decision making. So if you have some kind of agent, and it needs to make actions, and those actions are going to influence the future observations that it sees, and this encompasses a vast variety of problems that we face in machine learning, then we really are doing reinforcement learning. And the key is that success is measured by some scalar reward signal, and the aim of the game is to select actions so as to maximize future rewards. And so you'll see this kind of canonical loop here, which you've already seen in this in Daba, and I'm sure you'll see again, where there's some kind of environment represented by this world, and the environment is kind of feeding observations to the agent, and the agent in turn gets to take actions that influence the environment. And it's that fact that what the agent does actually influences what it sees from the environment that makes this a hard problem, because there's like delayed consequences to all of the actions that the agent takes. And it sees some reward signal, and the aim of the game is to maximize the sum of those rewards. So that's reinforcement learning. Deep learning, well, of course, we all know what it is, but what's the big deal? And I think the big deal is, again, it's something which is very general purpose. It's a general purpose framework for representation learning. Like, how can we build a general architecture for any objective, like whether that objective is for regression or classification, no matter what it is, can we build some kind of representation that achieves that objective in a very general way without domain knowledge, directly from the raw inputs that we feed into the system. And so that's the excitement about deep learning. It's like a modular approach where we can build something up with just a sequence of layers, and the whole system just works together so as to achieve that objective with minimal input from the designers. We no longer need to say what the special features are which are going to be used. It discovers those for itself. It discovers the representation that's going to be effective to achieve that objective. And so the excitement of DeepRL is really about putting these two things together to say, well, you know, what do we want? Well, I want, and I imagine many of you would also like to see, an agent that could solve any human-level task. So you give some task to the agent, and it can just go off and learn from that task and interact with its environment and do better and better and better until it succeeds in achieving the goal that you set it. And how can we do that? Well, we can do that with DeepRL by breaking this down into two parts, where reinforcement learning defines the objective, and deep learning gives us the mechanism for achieving that objective. And so if we put these two things together, the claim is, and the grand ambition of DeepRL is that if you put together RL and DL, you get this kind of approach for general intelligence, something which you put it into any new domain, you know, your agent gets born into some new world, and it learns how to succeed in that world. So that's the goal. We have some success stories. Of course, those success stories are very far off that end point, but we're starting to see steps. And those steps, I think, are what's driving the excitement and the progress that we see today. Okay, so in practice, what does it really mean? You know, how do you actually do this? How do you break this down into RL providing the objective and deep learning providing the mechanism? Well, you have to choose your objective. You have to say, well, in what way is reinforcement learning going to be broken down into some objective which can be satisfied by the mechanics of deep learning? And so three canonical ways that could be done would be by choosing to represent, using a neural network, the value function of reinforcement learning, the policy of reinforcement learning, or the model of reinforcement learning. And these are three different approaches which lead to three kind of branches of reinforcement learning known as value-based, policy-based, and model-based. And we'll see kind of examples of those, maybe not so much the model-based in this talk. And then the idea is that, you know, once that objective is well defined, like if we know that we're trying to build a value function and what it means to have an objective to make that value function good, or to make a policy good, then we optimize the loss function end to end. We optimize for that objective using the usual mechanisms of deep learning, such as stochastic gradient descent. And we do that end to end. And if we scale things up, then magic starts to happen. Okay, so I'm going to start with by going back in time. So deep reinforcement learning is a new phrase, but the ideas have been around for a long time. And so I think it's appropriate to go back and choose the first success story to be something from way back in the early 90s when Gerald Tesaro actually developed a backgammon program that learned to achieve superhuman levels of play just by starting off by playing games against itself and getting stronger and stronger and stronger until eventually it could defeat the world's strongest humans. And how was that done? And many of these ideas will seem familiar if you've been covering and watching what's been going on, for example, in AlphaGo. So what happened in backgammon was the whole backgammon game was represented by kind of flattening out the board. So in backgammon, you basically have these counters which get placed on these kind of positions like this, and the idea is that one side is trying to move its counters all the way in one direction, and the other side is trying to move its counters all the way to the end in the other direction. And so this board can just be flattened out into an input representation which looks something like this, which basically just gives input features saying how many white counters are there at each of these input locations. And so there might be a feature saying, are there 2 white counters at this location? And this would have a 1 for that particular feature, whereas there would be a 0 for the feature, are there 3 black counters at this location? And that whole thing gets flattened out into a representation with maybe like 100 or so inputs, and fed into what was, at the time, a very simple, shallow neural network with just one hidden layer. And the output of this thing was a value function, a prediction of who would win the game. Like, how good is it to be in a particular position? And that's a common theme, which we'll see again and again and again, which is that if you can evaluate the goodness of a situation using a neural network, it gives you a very powerful piece of technology, something which can immediately lead to strong performance in that domain. And so this was the idea, that this was the neural network in TD Gammon, and it was trained in the following way. So weights were started off completely random. Games were played by self-play. It would just play games against itself. And the training occurred by something called temporal difference learning, which I think you've heard about in the RL tutorials. But in the particular case of when you're playing these kind of games, you can simplify it down to understanding, what does it really mean to do TD learning? Well, it means that if you're in a position and you think you're winning, but then, you make a move and you kind of take that move, and all of a sudden it's like, oh no, I realize now I've made a mistake, I'm in a terrible position, now I think I'm going to lose. Maybe you see what your opponent did and how they responded, and suddenly you realize that the position you thought was winning is actually now a disaster and you're going to lose the game. Now, you don't need to wait until all the way to the end of the game to see that you actually lose it. You can already use feedback directly from that next step, and that feedback is known as temporal difference learning. In other words, you try and make your prediction that you had before consistent with the prediction that you make after you receive more knowledge, after you've taken that step, after you've moved one step closer to the end of the game. And so that's done just in a simple way. In TD Gamma, it was very straightforward, that this error was measured between your prediction that you had beforehand, before you took the move, and your prediction of whether you were going to win after making the move. And then the weights of the neural network were just adjusted in the direction that corrected that error. Basically adjust the weights of the value network to make it a little bit more correct with respect to what you subsequently thought, so as to make the predictions more self-consistent with each other. So remarkably, this very simple idea of TD learning in backgammon was extremely effective. There were no kind of special algorithms around it. In fact, the exploration mechanism was so simple, it was just greedy action selection. So the best action according to this value function was just selected just by using like one step of look ahead and picking the action that maximized this value function. That's how games were played out during training. There was no exploration at all, and yet backgammon actually still worked. It led to superhuman performance. And so I think that tells us several things. One thing it tells us is that this kind of game was actually easier than many others, that the dice provided a natural source of exploration and smoothed out the value functions and meant that this game actually became accessible to these methods way before subsequent ones. And what happened was that in 1992, TD Gammon went and actually defeated the human world champion by 7-2. At that time, it was actually using some expert features in addition to this kind of self-play training. But later results actually showed that those expert features could be removed. So this is a result from, I think, like 2009, a conference where Jerry Tesaro came back and showed what would have happened if you just let TD Gammon run with a slightly larger neural network than was possible originally, and without any expert features, just training from scratch. And it turns out it ended up even stronger. And so the principles of deep reinforcement learning were already in place. It already succeeded. It already led to superhuman play in certain domains. Okay, so that's the first success story. Let's roll the clock forward to 2015, and when Vlad Ni and others at DeepMind developed the DQN algorithm and applied it to the Atari emulator. So the idea of Atari was really to ask this question, can we build algorithms which are able to learn not just for one particular domain, but are general enough to be able to work in a really diverse set of different domains, whether you can have very different rules and qualities and properties in each of these different domains, and yet the algorithm should be general enough to learn to achieve human-level performance across all of them. And so this DQN algorithm was an example of that, and the idea was that we basically took our familiar reinforcement learning loop and we replaced it with the Atari domain itself. And so what happened was we didn't tell the agent anything about the way the Atari game went. So the Atari actually worked by having this kind of piece of hardware here, and you plugged in a different cartridge for each of the different games you were going to play. So if you were playing Space Invaders like this, you would plug in one cartridge, but if you were playing Pac-Man, you'd plug in a completely different cartridge. And we wouldn't tell the agent anything about the nature of those cartridges, so the cartridge was a black box and unknown to the agent. All it would see was the pixels, which came from the emulator, and the reward, the score, which came from the game. Just if we got more score, that would count as a little bit of reward. And the goal was to maximize the score given the pixels. And so this was done by basically using a deep convolutional network and using that convolutional network to evaluate, again, the goodness of each of these situations in the game of Atari, in one of these Atari games. So it would learn, if the agent was born into the game of Space Invaders, it would have to learn how to evaluate the goodness of one of these kind of screens. How good is it to be in this situation where there's a whole screen full of enemies in this situation, and I've still got my protection, and I've got my avatar there, compared to some other screen. It has to learn for itself how to convert those pixels into knowledge about evaluating that situation. And once it has that knowledge, it can use that knowledge to pick actions and play the game effectively. And so that was done, in this case, using a convolutional network, but the ideas could be applied to many other architectures. And so we can think of this, in general, as the following kind of approach, where, again, just like in TD Gammon, the heart of the idea is to represent a value function, in this case an action value function or a Q function, that estimates how good is it to be in a particular screen and pick a particular action with my joystick. And so what happens is all of these pixels are passed into this kind of neural network with some parameters W, and those parameters W are learned so that when you pass this state, these pixels into this kind of machinery, out pops an estimated score for each of the different actions on the joystick that you could take, and then you simply can use that to pick the best one. And so the main idea of DQN was to kind of adjust these Q values to respect something called the Bellman equation. And the idea of the Bellman equation is really, again, about consistency. It's another form of temporal difference update. And the idea is to say that if you take one step, you've got some kind of, think of there being some kind of optimal look ahead of how you could actually estimate the score in Atari. If you were able to look ahead all the way to the end of the game with some kind of look ahead tree, that would give you a way to estimate how good any action is. And so the idea of the Bellman equation is to say that if I just look one step ahead, if I take one step and look at one reward, my value after that one step of reward and doing a look ahead from that point should be the same as the optimal value from before taking that action. So the full kind of look ahead tree can be decomposed into one step, like the best step that I could take, followed by the optimal look ahead from that point onwards. And that look ahead is cached into this value function. It's cached into one number saying how good is it to proceed from this point onwards. And so this is the objective. It's plugged into the architecture to minimize this objective. We want to basically minimize a loss that is basically the difference between the right-hand side and the left-hand side of this equation, like a squared loss. And what we did was just a simple change to that straightforward idea, which was actually designed to remove correlations in the data. And so this was done by using something called experience replay. And so the idea was that when the agent actually took a step, instead of directly processing that step, it would feed that step of experience into a big database of experience. And what it would actually learn from would be some new experience that was sampled from that data set. So you could think of this as like incrementally building up a kind of data set for machine learning. And the data set consists of experience. And so what happens then is that the experience is sampled from this data set, and updates are applied to samples from this experience. And in particular, they're done in a way where we try to also deal with non-stationarity, and in that case, it was done by holding the target network fixed for a little bit. So that was the DQN algorithm. I'm sorry if many of you have seen these before, but I guess it's kind of fun to look at them in any case. Let me just see if I can launch some of these videos. And I think the main thing to take away from these is twofold. The first idea, which we see on the left, is that we can have a very simple strategy like Breakout, where it starts off completely with random behavior, and yet over time it can actually learn in a relatively small amount of experience to build up novel strategies and understand how to accumulate score to the point where over time it actually finds a way to build up strategies which maybe even the human designers didn't know about, like in this case breaking through the bricks to the left-hand side and getting the ball to bounce around at the top, which I think we'll see shortly. And on the right-hand side, I think the thing to take away here is there's a huge diversity in these games, that actually, some of them are kind of scrolling, some of them are side-scrolling, some of them are kind of pseudo three-dimensional. There's all kinds of different kind of dynamics and unexpected things happening in those games. And I think that's a lesson which tells us a lot about the nature of our algorithms. They should be able to deal with all of these different conditions and build up representations which are flexible and robust enough to be able to deal with all of these different situations. Okay, so, sorry. So when this was applied to Atari, we saw that we were able, at the time when this was first published, to reach close to human level of performance across a wide diversity of games, although there were a couple of games which were particularly challenging and proved hard to beat. But there have been a number of improvements since then, not just from DeepMind, but from all over the place. And here I'm just picking out 3 of them. And these 3 are selected because they're the ones which, over time, have proven to be the most important improvements, which have led to the largest change in performance over time. And so the first of them is to be multi-step. What does this mean? Well, it means to propagate rewards over n steps. Instead of just taking 1 step of experience and looking at how well you do after that, and kind of making yourself consistent with the prediction before 1 step and the prediction after 1 step, the idea is to take many steps. So to take n steps of experience and look at your predicted value after n steps of experience, and involve more of the real world along the way. And this has the property of, first of all, making us less reliant on the biases of our function approximator, because we've involved more steps of the real world. And so it kind of changes the balance between our own approximation and the reality of the real world. And it also can mean that the information can be transmitted more quickly from the future into the past. And so those properties lead to a huge difference in performance, and there's various different variants of this, including things like TD lambda and eligibility traces, which also allow information to be transmitted over long time scales. Key idea. A second idea is prioritized replay. This is a way to weight the experiences so that surprising events are replayed more often than kind of standard events. So, for example, if you see an event that transitions you from one screen to a completely new screen, or from one level to a new level, or from life to death, then these kind of events will be replayed much more often than the kind of really easy to predict events. And that kind of surprisingness is measured just by looking at the kind of error, the loss in this Bellman equation. And the third idea, which has been very effective across many different approaches, is distributional values. And the idea of distributional values is not just to measure the expected value of the score, which is what's traditionally done in reinforcement learning, but to measure the whole distribution over the score, and to track that distribution and to bootstrap from that distribution. In other words, instead of making the mean of the predicted score consistent with the mean of the predicted score after 1 step, we make the entire distribution of what we think will happen to the score consistent with the entire distribution of what we think will happen to the score after 1 step or n steps. And that idea is very powerful because it forces the representation to understand the world in a much kind of deeper level. In addition to that, it means that it deals with all kinds of scaling issues that kind of have plagued deep reinforcement learning, because now we're really just doing classification. We're just saying, you know, which of these bins is my value function going to live in? Am I going to estimate that I'm going to get 10 reward or 20 reward or 100 reward? And so it kind of reduces the problem to a slightly easier form. So those 3 approaches together lead to most of the differences we see between those kind of nature DQN plots that we saw earlier, which corresponds to kind of like this gray plot down here, and some of the more recent work, like this is the rainbow DQN up here. And so the performance has increased a lot, and it increases even more so if we start to scale up in terms of computation. So this is one particular approach that scaled up the computation and was able to train in just a few hours to reach a much higher level of performance relative to humans on a much harder kind of benchmark performance than was done in the original nature DQN. So we see that things still continue to scale, but also that new ideas are really helpful. It's always a combination of those 2 things. We want to push as hard as we can on our existing algorithms, scale them up as effectively as possible, and we also need new ingredients and new ideas, and hopefully people like you will be generating them. Okay. Now, you know, does this really matter? Does it matter in the real world? So I really like it when I see that people take ideas which have been developed in DeepRL and found innovative new applications that really have impact in the world. And so here's one example that I like. It's a news recommendation application. And so this was an experiment that was done by Microsoft Research in Asia. And it was done actually using real data on news recommendation from their application. And they showed that if you actually redefine the news recommendation problem, so what is the news recommendation problem? It's like you come onto a website and you want to know what's the news. But based on your history of what kind of news you've looked at in the past, you really want the system to tell you news that's personalized to you, news that's actually relevant and interesting to you as a person and not to the public in general. And so this has traditionally been done by kind of things like bandit algorithms or supervised learning, or approaches which are really just trying to predict whether or not you're going to click on that item of news. And the problem with those approaches is that they don't look at the fundamental issue that what you actually present to the user changes the user state. That by showing someone an article about some topic, you make them maybe less interested about seeing an identical article or something really similar later on, because maybe they're kind of they're saturated with that news story, or perhaps it's changed their state into being more interested in related stories, or you're really changing their journey through this kind of recommendation space. And so this particular paper really focused on trying to treat this as a reinforcement learning problem, trying to look at the whole journey that the user takes and trying to optimize for that journey by basically feeding in features about the user, feature about their context, features of the news article itself, and again, feeding them into a queue network, just as we saw before, and using that queue network to generate news recommendations to the user. And the one nice idea they had in that paper, in addition to applying DQN, was to use what's called a dueling bandits architecture, which basically meant that they when they actually came to generate a list of recommendations to the user, what they did was that they showed them, they kept their network, and then they perturb it. They kind of add some noise to it. So there's this network which is being used to kind of recommend things to the user, and it's kind of changed a little bit by throwing some noise into it. And then they see which of these networks works better, the original network or the noisy version of this network. And if the noisy one works better, then they move their original network a little bit in the direction of the noisy one. So they're basically running all these experiments to say, have these two kind of neural networks running side by side, making recommendations. One of them is a perturbed version of the other one, and if that one ever works better, then kind of use it to teach the other one to be better. And so this worked really well in practice. It significantly outperformed all of the baselines that have existed from traditional machine learning. And it demonstrates that really, these methods can be brought directly to bear on real-world problems. Okay. Success story number 3. This one is really, I found it hard to pin this down to just one instance of deep RL in robotics, because there's been a lot of great work from all kinds of labs. The Berkeley lab's been doing a whole load of things, and OpenAI, and people in Google Brain and at DeepMind, and there's things happening everywhere. So I really just tried to pull this one out as more of a theme of what I think is happening with deep RL in robotics. And what we've seen in robotics is that robotics traditionally has been very brittle. Like, you try to get your robot to walk and it falls over. And now what we're seeing is that there's a new and much more robust and flexible family of robotics algorithms which are able to actually learn directly from their experience and are able to perform in situations and using robots which traditional dynamics models wouldn't even be able to say anything about. And so I think this represents a success story which is kind of in the process of happening. I think we haven't reached the end of it, but I think it's emerging enough to represent a success story. And so I think we should understand, well, what are the issues in robotics that make it different from the rest of reinforcement learning? And I think there's two main issues that I'd just like to focus on, which make robotics hard, apart from just the pain of working with a real robot, which is always risky if you're going to get involved in this world. It's difficult to work with these things. And the first problem is dealing with continuous actions. So when you deal with a real robot, the actions it picks, it's not like in Atari where you've got, you either move your joystick to up or down or left or right. You now have a continuous space that this robot is working with, and if you just try to discretize that space, bad things happen, and it doesn't usually work very effectively. So continuous actions are the first point. And the second point is the scarcity of data. That often we're in a situation where we don't have a beautiful simulator like in Atari, which we can run endless simulations on and generate as much data as we're able to, given our computational budget. Every drop of experience really matters. And so the question is, how can you make DeepRL effective in this regime? So I'll address those in turn. So the first point is that continuous action reinforcement learning is now very, very effective. And there are numerous examples where this can be done very robustly and effectively. And the main idea which has been successful across DeepRL is something called the actor critic. So the actor critic really means, well, there's an actor, which is this essentially a policy, something which is going to pick the actions, pick these continuous actions, and a critic, which is basically back to our value function again, something which is going to evaluate the state and say, is the situation good or bad? And there tend to be two approaches to this, one of which is like the stochastic actor-critic, and the other is the deterministic actor-critic. And they basically use the same ideas and the same family of algorithms, but just kind of put together with slightly different slants. And so in the stochastic actor-critic, we have the actor, and you feed in your state, and it generates a distribution over actions. So in other words, you feed in a state, and it's going to give you randomly just a particular configuration that of the motor torques, for example, in your robot, like whether the robot's going to move in a particular way, and that thing's going to be stochastic. And so maybe it's typically going to move forward, but the way it moves forward might be a little bit noisy. And then there's a critic, which is evaluating the state, and the action now gets fed in. This noisy action that you sample has to be fed in now, because there's an infinite space of these. And it evaluates it and says, well, that particular action that just got taken by your robot, how good is it? How much reward is that going to lead to? Is your robot going to fall over now? Is it going to reach the big pot of gold at the end and succeed? And the other approach is the deterministic actor-critic, which is very similar, except now we have basically two parts of this, where first of all, the actor picks a deterministic action. So we pass it through this actor, and there's a neural network that picks a deterministic action. So one precise action, like it's always going to do this precise configuration, this continuous action, like move to this particular motor torques. And then the critic, it kind of gets sequenced on top of that, and the critic kind of evaluates that action to say how good it is. And then the idea in both cases is to update the critic by TD learning. So the critic gets updated in the way that we've seen so far in DQN and in TD Gammon. We're really just updating the value function to be consistent with itself. But the actor now, the main idea is that the actor gets updated in the direction of the critic. So if the critic says that the thing you're doing is really good, then we believe the critic. We don't look at the real world anymore. We kind of say, well, if the critic said that this particular action was the right thing to do, well, we should update our action to do more of the good things according to the critic and less of the bad things according to the critic. And that can be done in one of two ways. If we're in the stochastic world, it basically gets done by kind of multiplying these two terms together to give us our objective. The first term tells us, what's the likelihood, what's the log likelihood of this action in this state. So, is it, if I have this particular stochastic policy, is it likely to move me in this particular way? And then the other thing tells me, well, how good is it? And so this overall thing is basically saying, if things are good and they're likely, then I kind of multiply those together to say, do more of to make the good things even more likely and to make the bad things less likely. That's what it means to multiply those two things together. On the deterministic side, what we do is we kind of back-propagate the critic back through the actor again. And so basically what we're doing is we're saying adjust the actor in the direction that makes the critic happy. And in that case, we really have like a continuous thing which can be back-propagated all the way through. So we kind of go backwards from our critic, we back-propagate the gradient from that critic back into our actor. So we kind of know, which direction should the actor be adjusted so as to get more goodness according to my critic. So that's the idea of the actor-critic. I hope that was a little bit clear. That's probably my most technical slide, so you can kind of wake up again after that if that put you to sleep. And so we can have some videos now. So I really want to address these. So the following videos all kind of use variants of this actor-critic, and that's become quite well established in one of these two guises. And now I think the real question is, well, how can we make these approaches robust? How can we deal with the kind of scarcity of data issue? And so the first approach which has been used is to try and make the simulations which are used to train these things kind of more diverse. And so here's two examples of this. The first one, which is by Nicholas Heath from DeepMind, actually tries to make the simulations more diverse by having procedurally generated environments. And so the idea is that if you kind of have different obstacle calls every single time, then this can make the agent robust to all kinds of different things it needs to understand about, because maybe it will have to kind of figure out how to duck or how to run or how to jump. And these things emerge because there are many possible configurations in which the simulation is set up. The second idea, which comes from OpenAI, is this flexible kind of dexterous manipulation example, where they were able to train a robot hand to actually manipulate a dice to some target kind of location, to some target configuration. And the way this was done was also by kind of diversifying the simulation In this case, it was done by training in simulation, and then making the simulation kind of have all kinds of randomized configurations so that sometimes, the simulator would be changed or perturbed in different ways to make it likely that when it then moved to the real world, that the thing which happened in the real world was somehow represented in one of these many kind of randomizations that were considered, like different things and different lighting conditions, different dynamic variations, and so forth. Okay. I'm not sure if there's a good way to click out of these things. Once they're going. Oh, sorry. I stopped just at the fun part, sorry. Okay. So the second idea is to try and augment the data. So, if you don't have a simulator and you want to work directly from the data, what can you do? Well, the example on the left shows what happens if you're Google and you have a big budget, which is you can just augment your data by having lots of the things. So they created a large ARM farm, and they had many different instances of this robot arm, and they were able to train this robot arm farm to kind of learn how to manipulate all kinds of different objects. So this is very recent work that's come out of that lab this year. But what do you do if you don't have the budget or the access to many instances of the same object? Well, on the right-hand side, we see an example of what you can do, and this was done by Martin Riedmiller's lab at DeepMind. And this is an example of what you can do if you just have access to one robot, and instead of having to change the environment, the idea is to use the real environment that the agent's in. So this is, unlike the others, it's not kind of adding randomizations which don't exist in the real world, or changing the real world by multiplying it up and having many instances. This is about actually taking the real world which the agent's been born into and embedding many problem instances inside it to generate more data. So the idea is to say that even though there's only one of these robots, sometimes you try to learn about all kinds of different things from the same stream of data. So sometimes you want to learn, what's it like to pick up the green object. Sometimes you want to know what's it like to stack the red object on top of the green object. Sometimes you want to learn, how do you put a set of objects away into a container. And so actually, this is another way to mean that the same amount of data can lead to a much richer learning stream and allow us to learn a lot more from a lot less experience. And I think this is a really key idea, which I think we'll start to see more of. Okay. I managed to click off. Okay. So with apologies, the next success story is AlphaGo. And I've broken this down into two parts, AlphaGo and then AlphaZero, which is kind of following historically the development of AlphaGo to the point where it defeated the human world champion, and then going back to try and go back to research fundamentals and make the algorithm more general and rely less on external sources of knowledge. So, the game of Go is hard. It represents a challenge, and one of the reasons it represents a challenge is the size of the search space which we need to address. It's just one way to understand complexity, and it's a crude tool to understand how hard something is. But still, it's useful to understand this is why traditional approaches to search failed in the game of Go, because at each step there are something like 200 plus choices which can be made about what stone to place down next on the board, and the game lasts for maybe 200 plus steps. And so you have a search space which is roughly, you can think of as something like 200 to the 200. And this search space is too hard for traditional approaches to search to have any chance to kind of brute force their way through it. And so in AlphaGo, we address these issues by using two neural networks. The first of those neural networks was known as the policy network. The policy network, its purpose, if you like, was to actually decide which move to play. So you basically pass in a position. It was processed by a convolutional network of many layers, and out popped kind of move probabilities saying essentially, you should play this move with 70% probability and this other move with 30% probability. The second neural network is the value network. And the purpose of the value network is, again, as we've said before, to understand and evaluate the state. So in this case, the state is represented by the position of the Go board. We feed in the raw position of the black stones, the white stones, and the empty spaces. Those are processed by a deep convolutional network. In the original AlphaGo, it was 12 layers. And out pops a single scalar number, which is the evaluation of that position, to say, is essentially a prediction of whether the agent will win or lose from that position. This was trained in AlphaGo originally by starting from supervised learning. So that basically meant taking a data set of human positions in which in each of those positions a human expert had chosen the move, and using supervised learning to classify the human expert move. And so we basically trained on this human data set and made the policy network, trained it in such a way as to make the policy network predict the human expert move with high probability. And so that was supervised learning. But supervised learning in itself only teaches the network how to mimic an expert. It doesn't teach it any sense of understanding the game. So after that, it was necessary to improve this by using reinforcement learning. And that was done by playing games of self-play. At that time, by playing games with the raw policy network, not using any search, and playing many, millions of games with the policy network playing against itself, and applying reinforcement learning to that to estimate the value network. So in other words, the value network was trained to predict the winner of these games of self-play between the policy network and itself. And once we had these two different neural networks, they were used to make the search more effective in AlphaGo. So if we look again at this kind of exhaustive search space, this is just like a cartoon version with like a binary search tree and a tiny little 3x3 Go board. And the idea is to kind of say, well, what happens if we run this exhaustive search all the way to the end? Well, we can see even in this cartoon example, the search space blows up and we get nowhere. But the idea is that by using the policy network, we can reduce the breadth of the search tree. In other words, the policy network is recommending just, say, one or two or a handful of really promising moves, and we want the search to actually prioritize those moves above other moves. So in practice, this is done by sampling things according to the policy network. So if we sample according to those probabilities, it means that we see the moves which are considered good by the policy network much more frequently than the bad moves. And that dramatically reduces the breadth of the search tree. We can also reduce the depth of the search tree by using a value network. And so what does that mean? Well, it means that the value network is essentially caching the outcome of what would happen if you did a whole search in this game. So if you were to do a whole search from this point onwards, for example, there could be a search tree under this, and if you were able to run that whole search, you would end up with a number at the root node of that subtree. And that number would tell you, well, who's going to win or lose from that point onwards. And so the idea of the value network is it kind of caches the outcome of that whole search tree. It's kind of a prediction of what would happen if we were to run that whole search. And so we can kind of then fold away the necessity to run that whole search, because if we can predict it accurately, we no longer need to actually run that search. And that's the fundamental power of value functions in reinforcement learning, that they cache this kind of exponential look ahead into a single number that can be just looked up and accessed very effectively and efficiently. So, I think many of you have seen the movie, so I won't belabor this point, but AlphaGo went and played against Lee Sedol, the winner of 18 world titles, the greatest player of modern times. And it was an exciting time to be there, and AlphaGo won the match by 4-1. But it wasn't all plain sailing, as you may have seen in the movie. In fact, the game that we lost highlighted some of the deficiencies of AlphaGo, which was that sometimes it would get into these situations where it would misevaluate a position, and it could kind of stay delusional in its opinion about whether it was going to win or lose that game for maybe 10, 20, 30 steps of the game. And these kind of delusions were problematic. And so it led us to really go back to our fundamentals and see if we could progress AlphaGo further by improving the underlying machine learning behind it. And that led to the subsequent progress that I'm going to tell you about, by which we were able to remove these delusions and lead to essentially a player that I think had a 60-0, did have a 60-0 record against the world's strongest players subsequently. Okay, I think I'll skip this. You've all seen the movie, so this is a summary of the movie. Or hands up, would anyone like to see a brief recap of what was in the movie? Okay, yeah, can we play the movie then? I think we need sound for this. Sorry. Thank you. Feedback is always good. Shout at me more if I'm doing things wrong. I got one shout earlier about the humanoid, which I missed, but if there's time, I'll go back and show the end of that video, because it is quite funny. Okay, so for those who haven't seen the movie, this is like a summary of what happened when we went out to Seoul.
World's oldest this continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made mistake.
He's got to pronounce it a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Thank you. Sorry, that threw me so much that I've lost my presentation thing. Where's it gone? By the way, for those of you who haven't seen the movie, it's been, many people have asked me, was this something that we constructed afterwards, this movie? And the answer is no. We had no idea that actually the movie was even going to come to be. It was something where they were just originally taking some footage that was going to be kept for archival purposes. And it was only after the fact, once they came up to Seoul and saw how the events kind of panned out, that they decided that this would actually be something to make into a documentary. And so I was surprised as the rest of you when I actually came to see it for the first time. Okay, so the issues in AlphaGo that we saw in that match led to going back to the drawing board and trying to ask the question, can we develop machine learning algorithms which are principled enough that there is no ceiling to their performance, that if we run them and scale them and add the computation and the training time to these things, that they will just get better and better and better, dealing eventually with things like delusions along the way. And so this led to the AlphaZero algorithm. And one of the nice things about making something more principled is that it also becomes more general. And so AlphaZero ultimately was an algorithm which we didn't just apply to the game of Go, but to multiple different domains. So the main ideas of AlphaZero and how it differed from the original version of AlphaGo were that it didn't use any human data at all. So it learns solely by self-play reinforcement learning, starting completely from random weights. So this is back to the principles that we saw back in the TD Gammon example, but in a much harder domain now of the game of Go. There was no human feature here at all, no human features, no handcrafting. This only took the raw board as an input. And so together these ideas are very important because they facilitate the idea that if you take away all the human expertise, it makes it easy to transfer this algorithm to new domains and make it as general as possible to apply to something where maybe there isn't human expertise. It used a single neural network, so the policy and value networks were combined together into one neural network based on a ResNet architecture that was much more effective. And it was fully general, so we took away any special treatment that we used in Go. It was already a general algorithm, but there were some things in there like exploiting the symmetries of the Go board that we made sure that we could do without in this version of AlphaZero, so that it could be applicable to many domains. And so the main idea of the reinforcement learning algorithm in AlphaZero was for AlphaZero actually to become its own teacher. And so the inspiration, if you like, was to say, well, we used to learn from human experience. We used to learn from human data, samples where human players have played moves. And the quality of the human players really mattered to the performance of AlphaGo, but ultimately we couldn't really get enough experience of enough players of high quality to really make a difference to, once it starts to reach this superhuman regime. And so where can we get the best quality data? Well, the best quality data that we can produce actually comes from AlphaZero itself. So the idea is that if we can actually use AlphaZero, using the full search capabilities of AlphaZero, where it's actually doing a big look ahead at every step of the game to pick its actions, if we can actually use the actions which are selected by AlphaZero as training data for the next generation of neural networks, then we can end up with a much stronger algorithm. So AlphaZero becomes its own teacher, and so it goes something like this. I'm actually just going to change. I think someone mentioned that this other... here, is that clearer for people? Okay, good. So the idea here is that we've basically got AlphaZero playing games against itself. And we start off with some policy and value network, P and V for policy and value here. And so in each position, like starting with the empty position, in each position, there's some searches run using that policy and value network to generate a move. And then that move is played, and then a new search is run using the same policy and value network to generate a new move, and so forth, until eventually we get to the end of the game and we get an outcome. And that gives us some training data. And how do we use that training data? Well, we use it to train two things, the policy network and the value network. So first of all, a new policy network, this P prime, is trained to predict AlphaZero's moves. So the idea is that, again, from each of these positions where a move was chosen, we're going to train the policy network to predict more accurately, to basically make the policy network more likely to pick the move that was played by the whole of AlphaZero, by AlphaZero including its search. And then we move on to the next position, and we want to make that one also predict the move that was played by AlphaZero, and so forth. We're training on all of these positions in all of the games that were played by self-play. At the same time, we also train the value network to predict the winner of the game. So what that means is that in each of these positions, there was some value network, and we want that to accurately predict who would win that game. Like, will the value network correctly predict that black will win the game or that white would win the game? And so we look at these games of self-play, these games that were played between the whole of AlphaZero against itself, and we want the value network to be trained to really get a very close idea of, is this really going to, under best play, what we're trying to approximate is under optimal play, who would really win from this position? And the best proxy we can get for optimal play is using the whole of AlphaZero playing against the whole of AlphaZero, including search in the loop. And so this new value network is trained to predict the winner. And once we've done those two steps, we basically end up with a new policy and value network, this P prime and V prime, and that is used in the next iteration of AlphaZero. So getting ever stronger, this is now generating, we go through the whole loop again, and we generate stronger searches with stronger neural networks, leading to stronger move selection and more accurate estimates of who's going to win the game, which leads to a new generation of policy and value network and so forth. And so this is like an iterative approach. In fact, from a technical point of view, we call this approach search-based policy iteration. And it's really, if you go back to the reinforcement learning literature, it's building on some very fundamental ideas which have been around since Bellman in the, maybe 5 decades ago, which is the idea that we can break down reinforcement learning into 2 steps: policy improvement, making your policy better. If you have some way to evaluate the situation, you can use it to improve your policy. And policy evaluation, which means being able to estimate your value, estimate who's going to win from each of these situations. And the point is that in AlphaZero, we bring search into the loop. So when we're improving the policy, we use the search itself to make the policy much, much, much better. We don't just take like one step. We use a whole search tree, like the action which is picked by AlphaZero using its search, using look ahead to kind of look, to consider thousands of moves in many, many thousands of simulations and pick the best move, is much, much more powerful. Once you've run that search, you get a much better action selection than if you use the raw neural network. And so that's how we improve the policy. And similarly, the way that we evaluate the policy is by using search, to use this program with search in the loop playing against itself to give a much better estimate of the kind of optimal player of the game. Okay, little technical bit there again, but just for those of you who are interested. Okay, so how did this perform? Well, when we go back to the game of Go, AlphaZero actually achieved a remarkable level of performance. So we just ran this pipeline kind of continually. So it wasn't run, discrete iterations. It was just continuously running all the time, just kind of every time a new improvement came in, that was fed as quickly as we could back into the next generation of data. And actually, in just 8 hours, AlphaZero was able to surpass AlphaGo Lee, which was the version that actually defeated Lee Sedol in the famous match in Seoul. Now, when it says 8 hours, it makes it seem like that maybe was not so much computation. I should caveat that by saying this was 8 hours on the hardware which we have available, which was several thousand tensor processing units, each of which is like a very good GPU. But I think that provides some signal that maybe people without all of that hardware would be able to get some decent performance if they ran, maybe for a few weeks. And in fact, we have seen this in reproductions of AlphaZero, that people have been able to get very, very strong results without all of the hardware that we have. But one of the things I was most excited about with AlphaZero was its generality. Let me just point out that because it was starting completely from scratch, and starting from just from raw weights and discovering things for itself, AlphaZero was actually able to discover new knowledge for itself. So this is a process where it starts at the beginning of the game. It starts off playing completely randomly. But over time, it starts to figure out different patterns, things like opening patterns, corner patterns, tactical patterns, which have taken humans thousands of years to amass over time. And what was interesting was when we actually started to investigate it, we discovered that it actually identified known opening patterns that have been played by human expert players and discovered sometimes relatively recently in the history of Go. And then we found that it started playing those opening patterns more and more and more during training, suggesting that it figured out these really strong opening patterns. But then ultimately, it discarded them in favor of its own discoveries, which weren't known to humans when we asked the human professionals. And so, in a sense, it's like, at least in this closed domain of Go, it represents the fact that an AI algorithm can learn for itself to discover what's available in human knowledge, and in certain places exceeds those capabilities and come up with new innovations beyond what was there. Okay. So we wanted to see what happened if we applied AlphaZero to other domains. And so we kept this within the sphere of board games to begin with. And we chose as our next challenge computer chess. So chess doesn't have the game tree complexity that Go has, but it's challenging in another way. It's challenging because actually chess is perhaps the most studied domain in the history of artificial intelligence. And it represents, it was studied by Babbage, Turing, von Neumann, and it became what was known as the Drosophila, or fruit fly, of artificial intelligence for several decades of the early AI research. Because it was so popular, it was like kind of when people in genetics started doing their experiments on the fruit fly. And so computer chess was like this fruit fly that's how people figured out if their ideas were good or bad in AI for several decades. And actually, highly specialized systems have been very successful in chess. So it kind of represents what happens if you dedicate decades of handcrafting to build very specialized systems that just have been really, really overfitted to one domain and make that one domain as strong as possible. And so Deep Blue was an example. This defeated Garry Kasparov, the world champion, in 1997. But the state of the art continued to improve massively beyond that point. And most recently, we have indisputably superhuman chess playing programs, the best one of which right now is perhaps known as Stockfish. And I'll talk more about that shortly. We also looked as like a contrast and a control at the game of Japanese chess, or shogi, which is more complex than chess, and it has more interesting rules because when you capture a piece, you gain this extra move of being able to place down the captured piece back onto the board as one of your kind of extra moves, which really makes it a dramatically different game. And actually, it's only just like, I think, this year that people have achieved the level of top humans in the game of shogi. And so in all of these cases, state-of-the-art engines are based on something called alpha-beta search, a kind of look-ahead search based on minimax principles, but combined with enormous handcrafted evaluation functions that have been optimized by human experts and grandmasters over many, many years. And so if we look at the anatomy of one of these programs, we can pick out the current world champion program is something called Stockfish. And if we look at the kind of pieces of domain knowledge or extensions or heuristics in this program, this is taken from a website that kind of lists some of them. And each one of these represents a significant piece of research that was done over maybe 2 or 3 years by, or maybe a PhD's worth of knowledge that went into that program. And Stockfish is actually a beautifully engineered program, and so this is why it was so effective for many years and able to bring all of this knowledge to bear in a way which really led to very, very high performance. And what we were able to do in AlphaZero was basically remove all of them. So we didn't use a single one of these techniques, and we replaced them all with self-play reinforcement learning and self-play Monte Carlo tree search, which is the look-ahead technique that we use, which is also based on reinforcement learning principles. And then when we plugged this in, we found that actually in the game of chess, it took us 4 hours of training to surpass the level of Stockfish, by which we meant that when we played a match against Stockfish, in our initial match against Stockfish, we had 0 losses. There were quite a lot of draws, because you do get a lot of draws at high levels of chess, but we were certainly much, much stronger and won in some quite interesting games. And in Shogi, we also played against the existing world champion, and in 2 hours, we surpassed the performance of the strongest existing Shogi program. This demonstrates the generality to an extent within a certain sphere of applications of board games, and I think the jury is then out: can these approaches have impact on the real world? And so luckily someone else took up the mantle of doing this. Martin Segler and a group of researchers were maybe the first to demonstrate that there can be real-world impact of these techniques. And they applied the same techniques as we used in AlphaGo to chemistry. And they did something called retrograde analysis, where they were trying to basically ask the question, how can some compound be constructed, be synthesized from some known starting points? So if you have basically some ingredients in your lab, and there's a set of reactions that exist amongst, there's many, many thousands of known reactions. The question is, how can you kind of put those reactions together so as to create a desired compound? And so this has been a challenging problem and an open problem in chemistry for many years with a lot of real-world impact. They were actually able to reach state-of-the-art performance using essentially the AlphaGo algorithm applied to this kind of analysis problem. And so the moves in this case are basically applying reactions. So they start off with the end compound, this final compound that you want to create. And the moves are basically backward steps that you could take, like reversing, saying what would have happened if I'd reversed this particular reaction, and then from there reverse this particular reaction. And you can build up like a search tree from these possible reactions that were made, and apply the AlphaZero algorithm to figure out which sequence of reactions is actually going to lead to the optimal level of performance. And so they were able to reconstruct famous discoveries of recent compounds and how they can be synthesized in this paper. And they also compared by doing a study of humans, and they found that the humans couldn't differentiate between the solutions that were found by human experts and those that were found by AlphaChem. So I think, again, this demonstrates that an idea which was developed in a general way for games can have real-world impact. And I think it's nice to see that. In addition, I think we've seen a lot of progress within the game sphere, and also in producing the results of that we had in AlphaGo. Many strong programs now exist which are playing fantastic Go out there. It's been applied to many other games as well. Here's one example. And I met some people in this room who applied similar ideas to the problem of bin packing, and it's nice to see successful applications coming from out of the people at this Indaba. And so, exciting times when all kinds of things are happening. Okay. So, success story number 5, I've split into 2 parts. So this is now, I wanted to ask the question, do we have success stories in challenging multi-agent domains where we've got multiple agents interacting together to achieve something, large scale and significant at the level of the real world? And so the first part of this success story is based on work that was done recently by OpenAI on the game of Dota 2, which, for those of you who don't know, is like a sort of large-scale strategy game. And it's a 5x5 multiplayer game, and it's very widely played. It's one of the main esports with very large prize money pots of millions of dollars to the strongest Dota 2 player in the world at the competitions which happen. So it provides a great challenge for our AI methods. And we see that there's very rich strategies in the game, and so the game is challenging in certain dimensions. It's challenging because there are like 20,000 time steps per game. The way that they set this up resulted in basically they kind of discretized the problem, both in the action space and the observation space, so that so they're not presenting the actual screen in terms of the pixels to the program, but like a kind of flattened representation of all of the information that a human might see. That information gets kind of flattened out into a discrete list of actions and observations that gets kind of passed into the algorithm and passed out of the algorithm. And that contains 170,000 possible actions, of which about 1,000 are legal at any given step. And there's a kind of a vector of around 20,000 different observations that summarizes all of the information available to a human. So, from this whole screen of stuff going on. So it's a rich, complex game, and I just want to show you what happened. So this is the first time. Actually, for this one, we really need sound. Sorry, could we have sound for this? I'm just going to pause this and then. Let me explain first, and then I think you'll enjoy this video. So this was an algorithm known as Five. It's a self-play training algorithm that started from random weights. It was using an actor-critic algorithm, similar to those that I described earlier, with a particular variant known as PPO. The representation uses an LSTM network to represent the policy and the value. So this is kind of taking account of the history of what's happened before to deal with some certain aspects of partial observability. And some of the novel aspects that were used in this Five algorithm were this idea of playing about 20% of games were played against policies with old weights, so as to make sure you don't forget your old strategies. And there was a lot of handcrafted reward shaping based on expert domain knowledge. This made a big difference to their game. So what does that mean? It means that instead of just using the win or loss outcome of the game, they basically provide expert signals saying that if you do this particular thing, then that's a really good thing to do, and that led to big improvements. And they used, just like with the dice example, with the dice manipulation, they used domain randomizations, where they said, what would happen if the observation was slightly different to the one which you're actually seeing, or if the action was slightly different, or if the rules were slightly different, or and these various things. And that was able to give lots of different variation that they argue makes the algorithm much more robust to when it actually comes to play a real human player. In practice, they used slightly simplified game rules, so they took out one of the important stages of the game, which is like drafting. But the game rules are still immensely complex. So I'm not trying to take away from the achievement, which I think was really impressive. And so last year, they played against a professional human in 1 versus 1, and defeated a professional human. And then this year, they had a series of successes, but then they just lost in their kind of final challenge against a professional human team at the main competition this summer. And this video, which I'm just going to play, showed what happened when they took this 1 versus 1 version, and this showed actually the first time that a human professional was actually ever able to beat the system. And so this is just a little video that showed it. And if we could have sound for this, please, that would be great. I can't hear anything here, so what I like about this, we're about.
Whatever, man. I don't even need to block. Screw that. You're in the tower now, huh? Are you gonna get that last hit? Oh, he got it because I gave it to him.
Hang on, I'm at the wrong point.
The bot has me under his control.
Okay, sorry. Okay, so you get this kind of voiceover of the human playing, and this is at the end of the game when he's about to win the game.
Yes! 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 Oh, shit, yeah. Clutch! 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 he missed it.
Okay. So, so you see that I think it's a demonstration that it's a success story when the humans are actually so pleased to have actually defeated the AI that they're dancing up and down in their seats. Okay. So the second part of this success story is contemporaneous with that. It's some work by Max Jederberg and others at DeepMind. And this is on a game which is complex, a multi-agent game which is complex in other ways, Capture the Flag. It's also based on a very well-known esport, which is based on something called Quake 3 Arena, Capture the Flag. So again, one of the most played games in terms of esports historically. And in this case, things were done slightly differently. And so the problem is as follows. The idea is that you have agents who are wandering around. It's a fully three-dimensional kind of first-person view. And so the agents are actually seeing what's on the left here. So this is what the agent is actually seeing. So this is provided as the input to the agent. So it's receiving only pixels as its input. And so this is our visualization to help us understand what's going on in the game, but it's not seen by the agent. And the idea is that you have to go and kind of collect the flag of the opponent. You have to kind of get it out of the opponent's base, and you have to bring it back to your own base. And the person who does this is able to win the game and kind of score a point. And it actually leads to very sophisticated kind of multi-agent dynamics where there's all kind of different strategies that are known to be used by human players, like base camping and so forth, where you kind of have one of your agents kind of hang out near the base, and you use one of your agents as a distraction and so forth. And so it's a very rich, partially observed game. And the question is whether an agent, just by self-play reinforcement learning, faced only with the raw pixels of the game, can achieve high levels in this particular game, in this esport. And so, again, we were able to see. Let's see if I can. So one of the ideas which was used in this was similar to what we saw in the robotics sphere, where the environments were procedurally generated to make a very robust, diverse set of environments that are available to the agent, but always using the real rules of the game. So that's a slight different from the OpenAI randomizations. This is based on the real game, but with different maps that you could be based upon. So now the map itself is being transformed, and so each time the game is played, the agent is presented with a completely different map, and it has to see how well it can do with that map. And the maps look something like these things up here. And the algorithm, well, what's the algorithm? Well, the main idea of the algorithm was actually to have a two-stage training algorithm. The first stage of the algorithm is actually to decide on what internal reward should be used by the agents themselves. So think of it this way, that there's kind of these reinforcement learning agents at a low level who are optimizing for some reward signal, for some internal reward signal, but the internal reward signal that they're optimizing for is chosen by some higher level agent. And so this leads to like a two-level optimization where the high level is picking the goal and the low level is figuring out a policy, a strategy to execute so as to implement that goal. And this combination of high level and low level reward optimization and kind of policy execution led to a great deal of success in this domain. And so so is that clear to people? The idea is that this internal reward that gets used is kind of optimized by some high-level agent, and the way that it's optimized is so as to maximize the win rate. So in other words, it might be that directly going to pick up flags is a really good idea, and so we encourage the low-level agent to go and directly pick up the flag. But later on, it might discover that actually, not allowing the opponent to pick up the flag might be a higher incentive, and that might be incentivized higher later on in development. And then the lower-level agent is really figuring out how to execute the high-level strategy that's been selected, where the strategy is kind of decided and described in terms of these reward signals. Okay. And the low level is really executed in much the same way as we've seen in these other cases, using an actor-critic architecture to maximize those internal rewards, whatever they were. Another thing which was interesting in this approach was the network architecture that was used. So the network architecture incorporated kind of things which we might previously have thought of as like algorithmic ideas, things to do with like memory and hierarchy, things which we might have been tempted to devise completely new algorithms for. Instead, what was done in this approach was that the neural network was made sufficiently powerful to allow the agent to express ideas like memory and hierarchy for itself. In particular, it made use of a differentiable memory architecture. So those of you who've heard of the neural Turing machine or differentiable neural controller, that's the kind of idea that was used here, like a way to kind of store and retrieve memories, but in a fully differentiable way. And the second idea was a kind of hierarchical approach where there was like a fast and a slow time scale represented. So there was like this fast-ticking recurrent neural network, which was receiving the raw observations and picking raw actions. But there was also this slower ticking RNN that was operating every few ticks on top of that. And the idea was that this slow RNN allows it to kind of figure out this kind of high-level strategy, but in a way where these two timescales are made consistent with each other. And so the fast ticking thing has to be made consistent with the slow ticking strategy that's kind of discovered. And that was very effective in making this approach work much better. So I'm just going to play this one video, which kind of shows how this approach actually did in practice. So what we see is that there were these environments which were procedurally generated, and many different examples of these environments. And on the right-hand side, we can start to see the strategies which start to emerge from this. There was also this kind of outdoor variant of the map, which provided another source of training data and challenge for the agents. And then when this was put together, it was just training directly from these pixels by self-play alone, with multi-agents going on, each agent kind of learning for itself how to play in the context of all these other agents. So from each agent's point of view, the other agents become part of the environment, and each agent is kind of selfishly trying to figure out how to win the game. And I just wonder if I can skip forward a little bit. Here we go. Yeah, and what we saw then is that over time, the agent population, there's a population of these agents that we were sampling from and getting them to play against each other, and this population got stronger and stronger and stronger until it started to beat the level of strong humans who play this game. And actually, when tournaments were played against strong humans, so we benchmarked against strong human players and discovered that those not only would the agents defeat the humans, but that the humans actually, when rated, preferred collaborating with agents and were only able to beat agents if they actually collaborated with an agent on their side. So human versus an agent was kind of stronger than human with a human. The rest of this is just showing that all kinds of interesting strategies were discovered along the way, like those which are used by human players. So that, I think, represents arguably the second part of that same success story, that to show that multi-agent domains are now feasible at scale, starting from raw pixels and with large complexity like in Dota, and starting from raw observations like in Capture the Flag. And in both of these kind of spheres, I think there's hope that these, as with these other domains, that games will generalize to real-world applications very shortly. Okay. I have a little bit of time. So if you guys don't mind, we could take maybe a 5-minute break, and then I have a very short second presentation, which I'd really like to show to you guys. I've never done it before, but it's kind of like trying to pull out some of the principles of deep reinforcement learning, which I hope will be useful to some of you in your journeys through your research careers, and in terms of, I think it's basically 10 lessons that I believe are important to take away as to why deep reinforcement learning success stories have been successful, and what ideas to pull out that are important in the practice and principles of these things. So can I just get a show of hands? Because actually the alternative thing we could do is just have a bit of Q&A for the rest of the time. So maybe people who'd like to see the principles, put your hands up now. Okay. And people who'd like to do Q&A, hands up now. Okay. All right. We're going to take a 5-minute break to let me recover from that, and you guys to recover from that, and then talk about principles. Okay, so part 2. Now I'm going to try and pull things together by pulling out some really personal principles that I found useful in my research. They're principles I believe in. I think some of them are controversial. I hope you disagree with at least some of them, otherwise I feel like I will have failed. And I believe that these are some of the principles that lead to success in deep reinforcement learning. And if you ask another practitioner, they may give you a totally different set of principles. So you should always take this with a grain of salt. But I hope that they're useful to you and that they, to me, they really are fundamental and things which we really need to take seriously. Okay, so the first principle is about evaluation. And really, this is kind of like a meta principle. It's not about the algorithms themselves. It's about how we even set up the process so that we will make progress. And the point really is that, you know, the choice of evaluation really determines the direction that our progress will occur in. And so we need objective and quantitative evaluation. It's really risky if we start to rely too much upon our human intuitions into what's right and what's wrong. If I give an example, it would be in AlphaGo. We often saw situations where we kind of looked at these and we had human players inspect positions, and they would say, oh, no, in this position, AlphaGo is making a mistake. It's making a mistake. And then, you know, subsequent versions of AlphaGo would come along and keep making that same move, and eventually the human professional would say, oh, there's a new strategy there that they hadn't really figured out, and that actually there was just a completely different way to think about the position. Often it would be something like just completely ignoring the fight that the human thought was critically important and playing on the opposite side of the board. So we shouldn't trust our human intuitions about what's right for evaluation, but what we should do is to set up objective, quantitative evaluations and make sure that those are aligned to what we really care about. And so what do we care about? And this is maybe the most important single decision we'll make in the course of a project, like to actually set up this alignment and make sure it points us in the direction that actually will lead us to progressing in a way that will lead to us getting the results that we desire. At one point I really want to stress here, and I think we don't do a good job of in the deep reinforcement learning field, or indeed I think, you know, in my own work I think you know, we're at fault of making this mistake at times, is I think there is often a conflation between leaderboard-driven research and hypothesis-driven research. And I think the right thing to do is to decide in advance which of these we care about. Do you care about achieving a particular goal in terms of maximizing some score? Is that your objective? Is your objective to win at the game of Go against a human? Well, that's a kind of leaderboard-driven research. You want to get better and better and better until you can kind of overthrow that particular level of performance. You know, do you want to go and beat humans at Capture the Flag or Dota or whatever it is? That's leaderboard-driven research. And if you do this, you should be sure that the evaluation metric you choose corresponds closely to the end goal. Like if you want to beat a human, but you're only evaluating during self-play, using self-play, that's leading to a slight mismatch, and you need to be careful that mismatch doesn't pull you off in the wrong direction. And you should avoid subjective evaluation. The alternative is hypothesis-driven research. And the goal here is not to kind of just ascend up the leaderboard. The goal is to actually gain understanding. The goal is to really, as scientists, understand as well as we can a particular topic. And our goal is not to push the numbers up. Our goal is to say, well, I've really understood this well enough to really make a claim about the science behind this work that I believe will withstand the test of time. And when you publish a paper, that claim should be something that you believe will stand the test of time. And how do you do that? You know, what's the evaluation metric that will lead to that kind of success? And so one approach is to, you know, first of all, formulate a hypothesis, a really clear hypothesis. And so, you know, I'm just going to pull out one example here, and the science of this doesn't matter. The point is that, you know, the type of thing we're doing. You know, and so let me just read this out to say something like, you know, double Q learning outperforms Q learning because it reduces upward bias. And so this is a kind of scientific hypothesis that's verifiable, and where we're trying to understand the cause of something and not just look at the number, not just say, well, approach X is better than approach Y. And what should we do? Well, ideally, what we're trying to do is, if we're trying to understand whether this is true and whether this will withstand the test of time, we want to understand whether this hypothesis will also be true under a broad range of conditions. We want to make sure that it's, you know, is it just true when I run this using DQN with experience replay with a particular, ReLU nonlinearities in a feed-forward network? Or will this also be true when I change the architecture, when I change the optimizer, when I use an actor-critic architecture instead of a value-based architecture? We want to understand that this hypothesis is going to be true in a broad range of conditions as possible. And that's really science, to say, well, actually, I've made this hypothesis, I've evaluated it, and I've demonstrated that this cause is present in all of these conditions, and that verifies that this claim I'm making really holds true across a wide range. And so the goal then is to seek understanding rather than leaderboard performance. And one final point here, which I think is particularly important, which I think we do very badly in the field, is to compare like for like and not against the existing state of the art. Now, I have to say that this is controversial and that this may not help you in the current climate to get your papers published, because people really want to see you do better than the state of the art, and I understand that that's a drive in how people are reviewing papers at the moment. But I don't think it's the right thing to do. I think if we're trying to seek understanding, we really need to be comparing like for like, which means actually establishing a common setup and understanding, when I'm running my setup with this particular approach and comparing it to this other approach, like for like, using exactly the same algorithm, did I get the same, was the over-optimism worse here than here? Did I score more here than here? Like for like, so they're receiving exactly the same conditions. Because if we're not doing that, then we might be conflating the problem. It might, if, let's say you did better than the state of the art, and the state of the art was some number that you pulled from someone else's paper applied to the same domain. If you just compare to that number and you do better than it, maybe you did better because your idea was better, maybe it was because of your hypothesis, but maybe you did better because you happened to use a different CPU or GPU. Maybe you did better because you used TensorFlow rather than PyTorch. Maybe you did better because your hyperparameters were set in a more effective way. And I think conflating the comparison with the nature of that evaluation, what we really want to do is we want to gain understanding. And that understanding is always ultimately the thing which leads to long-term progress. And the final thing to say is, even when you want to do leaderboard-driven research, perhaps the right thing to do initially is to gain understanding by doing hypothesis-driven research. And that may be the approach which will drive you up the leaderboard, actually with the greatest gains, because you've accumulated an understanding that will take you further than short-term optimization. So I think both of these are important, and I'm by no means saying leaderboard-driven research is wrong. I think it's extremely important to push our algorithms as fast and as far as they can be, and I think this is actually, really one of the driving forces behind DeepRL. But we need both things and be clear about what you're doing. Okay, that's principle number one, like a meta principle. So good, I see skeptical faces already. I hope these are controversial, and we're going to get some good discussion after this. Okay, principle number two is scalability determines success. So what do I mean by this? Well, what do we mean by scalability? And so a definition of scalability that I'll use here is really to say that it's kind of its performance gradient with respect to resource. Sorry, I meant to have an image of this. But basically, it's kind of like saying that if you were to plot for some resource, and that resource, well, what could a resource be? A resource could be computation, like the amount of compute time you give your algorithm. It could be the amount of memory you give it. It could be the amount of data that you give it, which in reinforcement learning is typically the experience that it's seen. So if you give it more of that resource, does the performance increase? And what's the kind of nature of that curve? So you can kind of imagine that you might have one curve which starts really poor and it kind of slowly improves, but maybe there's some kind of cliffs and eventually it just goes up and up and up. And that's a kind of good scalability compared to something which maybe starts off with a lot of human knowledge in it, but then is kind of flat after that or even goes down. And what matters ultimately is the scalability of the algorithm. It's this kind of gradient over time. You want something which will just keep going up, and then if you were to start from this point and plug in your algorithm, it will keep going up. And if you start from this point and plug in that network and run your algorithm, it will keep going up, and so forth. And as you continue to increase those resources, it should just get better and better and better. And a good algorithm is one that eventually would be optimal given infinite resources. So if you could give your algorithm infinite memory, like infinite capacity for your neural network, that's kind of what we typically mean by memory. If you could give it infinite data, by which in reinforcement learning we typically mean experience, so you can kind of run your self-play all the way through, or you'll run against your environment for as much time as you have. And you have scale up the computation so you can use as much computation time as you want. If all of these things increase, we should be achieving optimality. And a lot of algorithms actually put something in the way of that. They introduce ceilings, and we should be very wary of ceilings on performance. Avoid ceilings. We want to make sure that we have algorithms which continue to scale. And if I had to argue, why has deep learning been successful? Forget reinforcement learning. Why has deep learning been successful? I would say it's because of this principle, that deep learning has found a recipe which scales effectively with three resources: the amount of data that you provide, the size of the neural networks, the memory that you provide to them, and the computation, so the time it takes to do your forward pass through the network. And if you scale up all of those three resources, what you see is that the curves just keep going up and up and up. And so there's no end to this. It's like if you could, we saw in TD Gammon curves which looked very exciting, which were able to kind of lead to superhuman performance. But now you roll the clock forward to AlphaGo, and we're in a regime where maybe we have 3 orders of magnitude more of each of those resources than we used to, and the curves kind of continue going up. They still look the same. And I would like to speculate that if we took AlphaZero and we projected it into the future, and we ran, once we have 3 orders of magnitude more resource, and we ran it from our starting point now, what would the learning curves look like? Well, they'd probably look just the same, but just zoomed out again. It would continue improving and improving and improving. And that's the property we should be looking for, and it's the gradient of that process of improvement that we should be maximizing. That's the thing which matters most. We just need to make sure we're effective with respect to our scalability. Okay. Principle 3, generality future-proofs our algorithms. So an algorithm's generality, well, what's that? I've defined that as its performance across different reinforcement learning environments. So an example of this would be something like the Atari work, where instead of working on just one domain, the algorithms were general enough to run across 57, widely varying domains, which all happen to share the same interface. Something would be even more general if it was able to work not just on Atari, but also on a robot, which is a different interface altogether. And what should we avoid? Well, we should avoid overfitting to the present task. And what we should be seeking are algorithms that will generalize to unknown future environments. Like, what do we really care about? Well, we really care about how far our algorithms are going to go in the future. We want to reach the point where, together as a research community, we crack the really hard problems of AI. That's our goal. And how are we going to do that? Well, we need to start thinking more about the future. What will future environments look like? And don't overfit to the current one which you're stuck on right now. And so, of course, the problem is that we don't know what these unknown future environments will look like. But we do know that it's quite likely that future tasks are likely to be at least as complex as current tasks, maybe orders of magnitude more difficult in certain regards, and that whatever difficulties are encountered in current tasks will most likely get worse, will increase. Those difficulties will become greater. And so the natural conclusion then is that we should test against a diverse but realistic set of RL environments. So we take a set of environments. We don't want to be testing against unrealistic, crazy stuff. I mean, ultimately, there's no free lunch, so you won't be able to defeat, any Turing machine environment in any realistic amount of time. But let's take, real-world challenges, interesting problems, make a diverse set, and challenge our algorithms against many of them. And if we can do that, then it's a kind of future-proofing. It's saying, well, if we can crack many of the problems which are represented by those domains, it's likely that we're doing a reasonable job that will help us to scale up to future environments. Okay, principle number 4, trust in the agent's experience. So what's experience? So experience in reinforcement learning, it's the data of RL. It's the observations that the agent sees, it's the actions that the agent takes, it's the rewards that it receives, telling it how well it's doing. This is the data of RL. So it's kind of this explicit sequence, if you like, this history of observation, reward, action, all the way from the beginning of the lifetime of the agent up until the current moment in training. And so the agent, well, it has this lifetime where it's born into this environment, and then its experience is what happens from its birth into this environment up until, at the end of its training. And that gives some stream of experience that gets accumulated over that course. And the argument here is that we should trust in that experience as the sole source of knowledge. That there's always this temptation to look elsewhere, to say, well, this isn't enough. that we could do better if we were able to go outside that sphere of knowledge. We'd do better if we could bring in human knowledge, expertise like human data, human features, human heuristics, human constraints, abstractions, human ways to manipulate the domain and make it easier or constrain it or change it. And the reason that temptation is there is because it always seems really, really hard to learn from experience. And it is hard. But we need to accept that it's hard. Like the core problem of RL is hard. We need to learn from this experience. It's the central problem of AI. And if we crack it, it's worth the effort, because this is the thing which will scale. Like experience is the resource that will scale as we go further and further, and our agents have longer lives and richer lives. We want that experience to scale up to the point that it will take us to richer lives and richer solutions. And so we have to trust in the content of that experience. Trust that the content is there, that there is sufficient content to be able to reach all the way to the strongest solutions to these problems. And I think this principle, we see it in things like AlphaZero, but also we see it in examples like Capture the Flag, Dota. These are examples where really hard problems have been solved by starting just from the experience and trying to push as hard as you can. And there are little bits around the edges with reward shaping and so forth, but the direction is clear, that if we trust it, we're able to scale and build on that experience, it's worth the effort. We can go a long way. So learning from experience, the argument is it always wins in the long run, because you always get more experience. Whereas if you start to put in all of this kind of human knowledge, it looks like it helps in the short term, but ultimately it ends up hurting you or not helping asymptotically. And so the important thing to do is, again, it's back to scalability. Focus on the resource which will increase over time, and that's the experience of the agent itself. Okay. This one really drives a lot of my research personally. Principle 5, state is subjective. So what does this mean? Well, what is state, first of all? Well, state is kind of the thing that the agent uses to make its predictions or to pick its actions. So the kind of representation of what's going on in the world right now, that it's built up over time, and this thing is kind of what's used to make its decisions. And so we should define this carefully then. Well, let's define state to be a function of the history, a function of this stream of experience of actions and observations and rewards. And we can build any function of that history we want, and we can call it state. And typically, we want that thing to be built incrementally. So we want to just, every step, we kind of build from the state you had before and adjust that state to give you some new state. And that's this kind of incremental update we have here. Just saying, and it leads to things like recurrent neural networks. And so really, this is saying nothing more or less than that the agent state is kind of the hidden state of a recurrent neural network, where the recurrent neural net, every step it's kind of fed in the latest observations and actions, and at every step it outputs an action to take in the real world, and maybe a bunch of other stuff like predictions about value functions or predictions about maybe modeling predictions about what will happen next in the world. But there's a bunch of predictions which maybe come out of this, and they also make use of this state. And so the question is, what's the nature of this state? And the argument is, for this to be subjective, is that it really is just like a recurrent neural network, that this thing it should be free to build its own representation of state. That in no way should we ever define this in terms of the real state of the environment. That the real world is kind of a fiction as far as the agent's concerned. That we shouldn't be reasoning about the real world that's out there. The only thing that matters is the agent's subjective view of that real world. It gets this stream of experience coming in, stream of observations comes in, stream of actions comes out. That is the reality as, from the agent's point of view. And the moment we start reasoning about some external reality, we've lost something, which is we've detached ourselves from the agent's reality, and we've started to claim that the real world works in a particular way. And that limits us, actually, because it forces us to reason about the world in ways which may not be natural to the agent, which may not contain the information that's important to the agent, which may focus on being forced to compute beliefs over external representations of the state, for example. And so an example of the wrong thing to do would be the POMDP view of the world, where the world is modeled in terms of a belief distribution over these kind of real states that exist in the world that's out there, rather than trying to build things up in a kind of agent-centric view, like from the agent's point of view. Okay, I'm getting there. Principle number 6. is to control the stream. So, as I've been pointing out, agents kind of live in this sensory motor stream of data. There's like observation streaming into the agent, there's action streaming out of the agent, and that's the agent's reality. And the agent's actions kind of influence this stream of sensation that's coming into it. Like if I choose to do something different, if I choose to swap these two things around in my hands, through that choice, I've influenced the sensations that I now will experience for the remainder of this talk. And those sensations can lead to dramatic consequences. And the goal of the agent is really to influence its stream in a way that kind of controls it. And so I would argue that what we should be setting out to do is to control kind of the features that the agent has, the salient aspects of the environment. So whatever is important to describe the agent's situation in the world, the features which are built up by the kind of representation learning. So we can think of these as kind of like the hidden state of the neural network. If the agent can control those things, if the agent can kind of push its own representation, if the agent can push one feature to be either high or low as it chooses, if it can choose to either experience wet or dry, if it can choose to experience hungry or full, if it can choose to experience light or dark, if it could choose to control all of the features that it has in this stream of experience, then it's able to control that whole stream of experience. And if it's able to control the stream, it's able to control its future. And if it's able to control its future, then it can maximize any reward which we choose to give it. And so the argument here is that we shouldn't just focus on maximizing reward, that the goal of an agent should be to learn to control the whole stream. Like it should be able to control the stream, control all these different signals which might be coming into it. And the more control it has over those signals, the more power it will have, and the more effective it will be when it actually comes to solving the task which we provide it. It will build up understanding. You know, a baby is born into this world, and it learns to, manipulate objects and to communicate with its mother and to do all these amazing things to locomotion, to get around in its world. And it does all those things, presumably not to maximize its success later on in life when it's 50 years old. The baby is doing it to learn how to manipulate its stream, perhaps, to control its mother, to get the mother to come and help out, or to pick up an object so it can make an interesting sound. This is what the baby is doing. And so we need to be doing that. So that's control the stream. Okay. Principle number 7, value functions model the world. So why use a value function at all? And I touched on this earlier in the talk when I was talking about AlphaGo and the role that the value network has in AlphaGo. And the idea is that the value function efficiently summarizes or caches the future. So it's like one number that kind of describes all of what will happen from that point onwards. And it's representing what will happen to the reward over that period of time. But it could equally be measuring something else. It doesn't just have to measure the reward. It could be any number that's being measured, any kind of cumulative number. It could be measuring how dry will the agent remain over the next hour. It could be measuring how hungry will it be in the future. It could be measuring will it be in this room in 1 hour's time. And so these value functions are efficiently summarizing a certain aspect of the future. And the reason they're efficient is that they're available immediately. So they're computed they're both represented and learned in a time which is independent of the length of that thing which is being predicted. So even if you're making a prediction about what will happen over the next hour or the next day or the next year, that prediction is being formed immediately. You don't have to wait for a year to see what will happen. You don't have to imagine a year's worth of primitive actions to see what will happen. You can actually invoke that value function and query it immediately. And similarly, when you learn about it, the magic of temporal difference learning enables you to learn about it without having to wait for that whole year to elapse before you can actually get feedback. You can take one step and immediately at the next second or the next moment receive feedback that helps you to train that value function. So value functions are efficient representations of the future. And so the idea then is that if we learn many of these things, then this helps us to efficiently model many aspects of the world, to control the stream. And some of the aspects we might wish to control could be things like subsequent state variables. So this could include many of the things we consider when we start building models at multiple timescales. And so we should avoid modeling the world at a primitive time step, and value functions provide one tool for doing so. And so really this is a natural follow-on from the previous slide, which is, how do we control the stream? And one way to control the stream is to build many, many value functions for all the different aspects of the stream that we want to control. Like, what's the optimal value function for the baby? What's the optimal value function for whether it's going to hear a bell or not? And then it can learn to manipulate its toy in a way that will make the bell ring, or it can learn to get the mother to bring the toy over, or whatever it is, by crying. Okay. I'm getting there. Principle 8, planning. Planning is learning from imagined experience. So really, this is about a kind of symmetry that we can exploit. It's a symmetry between learning and planning. That, we like to think of these as different problems. We like to think that learning is the problem of kind of, the agent experiences, takes actions in the real world, and how can it update its policy or its value function based on what happens in the real world. But it's equally possible to, and we think of planning as the problem of, what happens, how can the agent use computation? How can it think in its own head so as to do better, to improve its policy? And the main idea is that we can actually convert the planning problem into a learning problem by learning from imagined experience. So we can use our kind of, some kind of model to sample trajectories of states from the model. And so this is essentially the heart of what's behind planning in AlphaGo. It's really this process of Monte Carlo tree search, which is used in AlphaGo. It really is sampling trajectory of states and then learning from that imagined experience. And the way that we learn from that imagined experience is using the same RL algorithms that we apply to real experience. So Monte Carlo tree search is actually, what is it? Well, it's the first algorithm which you find in an introductory textbook on reinforcement learning is table lookup Monte Carlo control. And so the search algorithm which AlphaGo uses is actually that first most elementary learning algorithm, but applied to imagined experience that starts from now. Basically, the algorithm starts to imagine sequences of experience, and then it learns from those experiences which states in its search tree are good and which states in its search tree are bad. And that enables it to search extremely efficiently. And why is this so efficient? Well, it's because it focuses our value function approximation. It focuses the resources that we have available to bear on this special moment that the agent is facing, which is the special moment now. Like right now, it really matters to me, what will happen next. I'm worrying about things like, how to talk and how to point the laser pointer. And right now, it's not relevant to me how to climb up a mountain in the Himalayas. But if next year I find myself in the Himalayas trying to climb a mountain, which I'm not planning on, by the way, in case you're worried, then it would really matter to start planning and imagining what would happen from that point onwards if I was going to put one foot and step into a crevasse, or if I was going to put a step onto a solid rock. And at that point in time, I don't want to be wasting my simulations imagining what would happen in a lecture theatre in Stellenbosch. Okay, so focusing on the moment now, and that's what learning from imagined experience means. Okay, second last one. Principle number 9, empower the function approximator. So we are lucky to live in a time where we have really powerful function approximators. We have these incredible neural networks. We've had incredible research from the deep learning community showing the amazing things and architectures and models which are available. And often, those architectures include ideas that kind of facilitates sort of things which might traditionally have been thought of as part of the algorithm itself. So things like representations of state. You don't have to have an algorithm that's kind of deciding what your state is. You can instead have something like a recurrent neural network or an LSTM or a memory architecture. We don't need to think about something like memory, something which is storing what the agent has seen and then storing it in some lookup table and then later having an algorithm that decides what to retrieve and how to make use of it. Instead, we can push that into our network architecture and have things like differentiable memory. Instead of building search trees and building things like Monte Carlo tree search, we can even push those things into our neural network architecture. And turns out you can do all of the things which you could do with the search, you can do by devising a neural network architecture that can learn how to search for you. Hierarchical control. We don't need to build algorithms that decide to have a slow time ticking level and a fast time ticking level. Instead, we can push that into our neural network architecture. And in fact, the capture the flag example included rich representations of state, differentiable memory, hierarchical control, and there was nothing different in the algorithm to deal with those things. It was all pushed into the neural network architecture. And so the principle then is to try and push algorithmic complexity into the network, like into the function approximator. So we kind of want to reduce the complexity of the algorithm. In other words, how the parameters are updated. That thing should be really, really simple. It should just be based on the experience the agent's seen and the other principles we've seen so far. We just want to make the agent understand its world and get more reward, or to control the stream, or whatever we're trying to do. But we want to really increase the expressiveness of the neural network architecture, the function approximator. So what the parameters do should be really rich. So we want the parameters to be updated in a really simple way, but to do amazing things. And that principle can really take us a long way. Okay, final principle. Principle number 10, learn to learn. And this one I really see as just being kind of an inevitable march of progress in the history of AI. So if we look at the history of AI, maybe we can break it down into 4 generations. And so the first generation of AI we could think of as like good old-fashioned AI, where there were kind of, the predictions that were made or the knowledge that was put together was all handcrafted, and nothing was learned. Like it was literally, people built expert systems, and they just put their knowledge into the system, and that's what it knew, and that's what it would say, and that's what it would predict. And so if something was good, it was good because we told it it was good. The second generation was, the advent of machine learning with what we could call shallow learning, things like support vector machines and so forth, where there would be handcrafted features or feature space, something which would say, these are the features which we as humans decide are really important to represent the problem, and then predictions were learned by kind of a shallow representation on top of that. There was like you just build a linear combination of your features, and that's your prediction of whether this thing is good or bad. And so that was like the second generation of machine learning. The third generation we could think of as deep learning, which is really that the algorithm, the way in which the parameters are updated is kind of handcrafted. So we handcraft our optimizers by doing things like Adam or Momentum or whatever it is. We kind of we handcraft the targets which we use when we do reinforcement learning. Do we use TD lambda? Do we push n-step returns in there? Do we learn about particular internal rewards which are provided? Do we handcraft the reward, as was done in the Dota 2 example, to say that certain things are desirable and other things are undesirable? And we handcraft the architectures, like the neural network architectures. The outline of the architecture is devised by humans. But given all that, deep learning does everything else for us. It learns the features, and it learns the predictions end to end. So we got rid of the learning the features. It's now able to figure out what's important, what the representation should be, and use those features to build up the predictions end to end. And I think what's been exciting over the last couple of years is starting to see this fourth generation start to emerge, which is meta-learning. And meta-learning you can kind of see as handcraft nothing. That what happens if we could learn the algorithm and the features and the predictions end to end? And why should we think this is successful? Well, for the same reasons that each step has been successful and has led to a dramatic improvement historically, is because every time we handcraft something, we're limiting the capability of the algorithm to learn for itself something better than the knowledge we put in. It's the kind of knowledge acquisition bottleneck all over again, that it's really hard for us as humans to figure things out and put them in there. And it's kind of like the hubris of us as researchers to think that we kind of know better than the system about how to do something. And so if we can empower our learners to learn for themselves how to do these things, ultimately, I believe we'll end up with the most effective solutions. Okay, so that's it, 10 principles. I hope that at least one of those is useful to you. I hope that at least one of those is extremely objectionable to you and we can have some lively debate. And I hope it was interesting, and thanks a lot for listening.